હેલો એવરીવન, આપણે લાસ્ટ લેક્ચરમાં એસપીટી ટેસ્ટ જોયો તો. હવે આપણે ઇનડાયરેક્ટ સબસોઇલ એક્સપ્લોરેશનની વાત કરીએ છીએ તો એમાં કોન પેનિટ્રેશન ટેસ્ટ પણ આવે છે. તો હવે કોન પેનિટ્રેશન ટેસ્ટના બે ટાઈપ છે, સ્ટેટિક અને ડાયનેમિક. હવે કોન પેનિટ્રેશન ટેસ્ટ એસપીટીથી ડિફરન્ટ શું પડે છે એની વાત કરીએ તો કે ભાઈ એસપીટી ટેસ્ટ કરીએ આપણે ત્યારે આપણે બોરહોલ કરવો પડે છે ડિઝાયરેડ ડેપ્થ સુધી જ્યાં આપણે ટેસ્ટિંગ કરવાનું હોય ત્યાં. બટ કોન પેનિટ્રેશન ટેસ્ટમાં કોઈ પણ ટાઈપનો બોરહોલ કરવાની જરૂર પડતી નથી. પેનેટ્રોમીટર છે એ ડ્રાઈવ કરવાનું હોય છે જમીનની અંદર બાય મિકેનિકલ ઓર મેન્યુઅલ, અને ડિઝાયરેડ ડેપ્થથી આપણે જે કંઈ બી આપણે ડેટા કલેક્ટ કરવાનો છે ટેસ્ટિંગ માટેનો તે ડેટા કલેક્ટ કરવામાં આવે છે. આ સાઉન્ડિંગ ઇક્વિપમેન્ટ છે. સો આપણે એમાં હવે સ્ટેટિક કોન પેનિટ્રેશન ટેસ્ટ વિશે જોશું. પહેલાં static cone penetration test, also called as Dutch cone test. Static cone penetration test have a own code, own methodology in IS 4963 Part 3 1976 method of subsurface sounding for soil Part 3 static cone penetration test. Penetration resistance of soil is measured in this method. Give accurate result in soft or loose soil like sand, loose sand, layered deposit of sand, silt, and clay as and clays deposit. જનરલી આપણે એસપીટીની વાત કરીએ તો એ કોહેઝન લેસ સોઇલમાં જ યુઝ થાય. ને જો આપણે સ્ટેટિક કોન પેનિટ્રેશન ટેસ્ટની વાત કરીએ તો એ કોહેઝન અને કોહેઝન લેસ બોથ સોઇલમાં આપણે એનું યુઝ કરી શકીએ છીએ. કમ્પેરિઝન બિટવીન એસપીટી એસસીપીટી ને એસપીટી ટેસ્ટ કરતાં કોહેઝન લેસ સોઇલમાં રિઝલ્ટ સ્ટેટિક કોન પેનિટ્રેશન ટેસ્ટ એક્યુરેટ દે છે. Test up to depth of 15 to 20 meter can be complete in a day with manual operation of the equipment, making it one of the inexpensive and fast method of sounding available for investigation. મેન્યુઅલની વાત કરીએ તો 15થી 20 મીટરની ડેપ્થ સુધીનું આપણે ટેસ્ટિંગ પર ડેમાં કરી શકીએ છીએ. મેન્યુઅલી ઓપરેટેડ છે. મિકેનિકલ ઓપરેટેડ તો બહુ ફાસ્ટમાં વર્ક કરી દે છે. તો આપણે એમ કહી શકીએ કે એસપીટીની કમ્પેરિઝનમાં આ ટેસ્ટ ઘણું ફાસ્ટ રિઝલ્ટ આપે છે આપણને. ટાઈમ સેવિંગ છે ને કોસ્ટમાં પણ ઘણું બધું સેવિંગ કરે છે. નાવ હવે આપણાના એપરેટસ છે એ જોશું. બેઝિકલી ધીસ ઇઝ ધ પેનેટ્રોમીટર which are in figure. The apparatus consists of steel cone, a friction jacket, sounding rod, metal tube, a driving mechanism like a manual or automatic machine કે મેન્યુઅલ બેમાંથી કોઈ બી એક ડ્રાઇવિંગ મિકેનિઝમ હોય છે. એન્ડ મેઝરિંગ ઇક્વિપમેન્ટ સોઇલ રેઝિસ્ટન્સ મેઝર કરવા માટેનું ઇક્વિપમેન્ટ હોય છે. સો આ ફિગરમાં આ કોન એસેમ્બલી છે ને આ ફ્રિક્શન જેકેટ છે. પણ એકચ્યુઅલીમાં આ નીચેની ફિગરમાં જોઈ શકો છો તમને આ કોન એસેમ્બલી આ ટાઈપનું હોય છે. એ ફ્રિક્શન જેકેટ આરે કનેક્ટ થાય છે. આ નીચે આ કોન એસેમ્બલી છે. આ બ્લેક છે એ ફ્રિક્શન જેકેટ છે. આ યલો કલર છે મેન્ટલ ટ્યુબ છે. એ જનરલી વર્ટિકલી સ્ટ્રેટ રહેવાનું ટ્રાય કરે છે કે ભાઈ કોન એસેમ્બલી છે એ સ્ટ્રેટ જમીનની અંદર જાય એનું કામ છે. મેન્ટલ ટ્યુબનું એ કામ છે. અને સાઉન્ડ રોડ છે જે મેન્ટલ ટ્યુબ સાથે કોન એસેમ્બલી સાથે કનેક્ટેડ છે, જેનાથી આપણે રીડિંગ ઉપર ટ્રાન્સફર થાય છે. જનરલી સાઉન્ડિંગ રોડ છે તેની આપણે 1 મીટર કરીને જેમ ડેપ્થ વધતી જાય છે એમ એની લેન્થ વધારતા જતા હોય છે. આનો વિડીયો પણ એક હું હશે આની સાથે, એમાં તમને વધારે ખ્યાલ આવશે કઈ રીતે આ ટેસ્ટ કન્ડક્ટ થાય છે. The steel cone shall be of steel with a tip headed in the shell as apex angle of 60 degree and overall base dimension of 35.7 mm given a cross section area of 10 centimeter square. આજે સ્ટીલ કોન છે જે આપણો એનો જે ફ્રન્ટ છે એ 60 ડિગ્રી હોય છે, અહીંયા મેન્શન કરેલું છે. The friction jacket shall be high carbon steel. Sounding rod is a steel rod of 15 mm diameter which can be extended with the additional rod of 1 meter each in length. સાઉન્ડિંગ જે રોડ છે તેની જે મુજબ ડેપ્થ આપણી ઇન્ક્રીઝ થતી જાય એમ મુજબ એનું ઇન્ક્રીઝ થતું હોય છે. The mental tube is a steel tube means of guidance the sounding rod which goes through it. It should be 1 meter in a length with plus coupling. મેં તમને હમણાં જ વાત કરી કે સ્ટ્રેટ રહેવાનું ટ્રાય કરે છે જે આપણી મેન્ટલ ટ્યુબ અને મેન્ટલ ટ્યુબનું કામ સ્ટ્રેટ ટૂંકમાં આપણું જે કોન છે સ્ટ્રેટ જમીનની અંદર રીડિંગ પરફેક્ટ આવે ગાઈડ કરવાનું કામ છે મેન્ટલ ટ્યુબનું. The driving mechanism should have a capacity of 20 to 30 kN for the manually operated equipment and 100 kN for mechanical operated. The hand operated may be provided with handle on both sides of the frame to facilitate given by the 4% for load greater than 20 kN. For the engine driven equipment, the rate of travel should be such as that the penetration obtained the soil during the test 10 to 15 mm per second. Process. The test process for determining the static cone frictional resistance consists of pushing the cone along through the soil strata to the best to be tested. Then the cone and friction jacket and finally the entire assembly is sequenced and notice the respective resistance in the first two cases. The process is repeated at predetermined interval. After the reaching the deepest point of the investigation, the entire assembly should be extracted out of the soil. The result of the test shall be represented in 2 gram cone resistance with depth in meter. Small qc is equal to qc upon ac. Small qc છે એ cone resistance છે, capital Q છે force required to push the cone and AC છે cross section area of cone. Frictional resistance માં FC is equal to QF upon AF. એમાં FC છે frictional resistance of the friction jacket, QF છે force required to push the friction jacket and AF છે surface area of the friction jacket. આની આખી પ્રોસેસરનો વિડીયો છે ના. હવે આપણે તે વિડીયો સ્ટાર્ટ કરશું.
Each year, the Louisiana Department of Transportation and Development spends millions of dollars to design, construct, and maintain its highway system. A significant portion of these funds is needed for the foundation systems. All structures, including bridges, pavements, walls, embankments, and buildings, are ultimately supported by the existing terrain. For safety and economy, the design of these structures is based on the properties of the building materials and upon the properties of the foundation materials in the natural ground. Therefore, the designer of these structures must know the surface and subsurface soil conditions in order to create safe and efficient designs. Geological conditions are such in Louisiana that a thorough investigation of subsurface materials is vital to the design engineer. Because dense bearing layers are often encountered well below the ground surface, bridge structures in Louisiana are supported on deep foundations. Piles carry the superstructure loads deep into the ground, either in end bearing or by side friction. The safety and stability of pile supported structures depends on the load carrying capacity of these piles. Current DOTD practice of pile design is based on a static analysis using soil properties obtained from field and laboratory testing. Taking deep borings is an expensive, time-consuming process. Obtaining samples for the design of deep foundations involves drilling into the earth to retrieve the soil found at various depths for the purpose of determining its strength properties. To recover undisturbed samples and perform standard penetration soundings, wet rotary drilling equipment is needed. Standard equipment includes a drilling rig, a water truck, a utility truck, and a carryall. Wet drilling is always messy and sometimes hazardous work. Drilling mud is pumped into the hole to provide stability for raising and lowering sampling tools to the required depths. Shelby tubes are used to retrieve undisturbed soil samples. These samples are extracted and carefully packaged for shipment to the laboratory. When dense materials are encountered, standard penetration tests, or SPTs, are conducted. Penetration soundings involve driving a steel rod into the soil to determine the resistance in blows per foot. Boring logs are manually kept in the field to record depth of sample, visual classification, and SPT or pocket penetrometer strength. Depending on the depth of the exploration, crews are often capable of completing 2 borings per day. Laboratory testing of the soil samples includes soil classification, soil density, Atterberg limits, unconfined compression tests, and triaxial tests. DOTD district crews perform the majority of subgrade soil surveys used in the design of pavement structures. Each district operates a boring rig capable of recovering disturbed soil samples. Samples are collected as the auger is advanced into the ground. A drilling log is maintained in the field to record location and depth of sample. Samples are placed in moisture-proof containers for testing in the laboratory. Laboratory testing includes soil classification, Atterberg limits, sieve analysis, and moisture content. Department engineers use the subgrade soil survey produced from these borings for the design of pavements. Besides subgrade properties, the design and evaluation of pavement structures needs a substantial amount of supporting data such as traffic loading characteristics, environmental conditions, and materials properties of the base and subbase. Currently, empirical correlations developed between field and laboratory material properties are used to obtain subgrade performance characteristics. These correlations do not satisfy the design and analysis requirements because they do not address all possible failure mechanisms in the field. Most of the subgrade properties used in the correlations do not represent the strength conditions of the subgrade, environmental variability, or the repeated traffic loading on the pavement. Because of the considerable time and expense associated with conventional exploration operations, there is a need for more rapid and accurate site characterization techniques. The Louisiana Department of Transportation and Development and the Louisiana Transportation Research Center operate 2 types of electronic cone penetration systems. The cone penetration test, or CPT, essentially consists of pushing an electronic probe into the soil at a rate of 2 centimeters per second. The device is equipped with a load cell at the tip to measure resistance offered by the soil during intrusion. It is also equipped with a friction sleeve to measure the local friction between the surrounding soil and the shaft of the probe. The CPT tip resistance and sleeve friction data can be used to determine soil types along with a variety of engineering soil properties. Both DOTD and LTRC operate large cone trucks with reaction capacities of 20 tons. These trucks are used to gather soils information as deep as 200 feet. Besides the standard 10-centimeter cone and a larger 15-centimeter cone, other cones available measure pore pressure and electrical resistivity. A cable that is threaded through the push rods transmits the information. A hydraulic ram pushes the probe into the ground at an average speed of about 1 meter per minute. Up to 200 meters of penetration soundings can easily be made with this equipment in 1 day, 7 times faster than conventional drilling. Readings, taken every 2 centimeters, are viewed by the operator in real time on the computer screen. Results are available immediately and can be stored in the computer or saved on a disk for use at a later time by design engineers. The cone penetrometer test, or CPT, has been used to set pile lengths on many DOTD projects since the 1980s. On the vast majority of projects, CPT technology has been limited to identifying dense sand layers required to support end-bearing piles. The CPT soundings have traditionally been taken during the construction phase to supplement a full complement of borings already in the plans. Results of the LTRC study, evaluation of bearing capacity of piles from cone penetration test data, has demonstrated the capability of CPT methods in predicting the ultimate load carrying capacity of square PPC piles driven into Louisiana soils. A Windows-based computer program has been developed for pile load capacity prediction with CPT data. This now allows DOTD engineers to use CPT technology to set lengths for both end-bearing piles and friction piles. Utilization of the CPT during the design phase can drastically decrease the number of soil borings and reduce the cost and time required for subsurface characterization. It is well documented that CPT data can be obtained faster with less cost than conventional soil boring data. CPT soundings taken at closer intervals than traditional borings will provide more details on soil stratification and therefore less potential for error. Using CPT data can reduce the number of borings required, and correlation with the test pile can provide more accurate pile lengths for additional savings. LTRC has recently miniaturized and adapted this proven CPT technology for highway subgrade characterization and pavement design. A continuous intrusion miniature cone penetrometer has been implemented in a four-wheel drive vehicle. The vehicle provides for the leveling and gross weight needed to react during cone penetration. A novel feature of this new in-situ testing vehicle is a Caterpillar-type continuous push device. It is powered by a hydraulic motor for advancing the cone penetrometer. The cone rod is a 1/2 inch diameter stainless steel coil tube. The coiling thrust rod eliminates the need for threaded connections. It has a 2 centimeter electronic cone penetrometer attached to one end and a cable connector at the other. This one-man operation greatly increases productivity and serviceability. The system may be used to test on natural ground, beneath existing pavement through an access hole, and even on side slopes. To provide greater mobility and site accessibility, the system can also be mounted on smaller four-wheel drive or tracked vehicles. A laptop computer is used for data acquisition, processing, and analysis. The computer is equipped with interface modules that convert analog input signals to engineering units. As with the larger cones, the mini cone can be used to provide a variety of soil properties. The mini cone equipment has been implemented on several DOTD projects for the identification of soft subgrades, slope stability analysis, and pavement design. The LTRC research project, investigation of the applicability of intrusion technology to estimate the resilient modulus of subgrade soil, has developed a prediction model to estimate the resilient modulus property needed for pavement design. The prediction model correlates the resilient modulus to the cone penetration test parameters, basic soil properties, and in situ stress conditions of the soil. LTRC is continuing efforts to validate the prediction models. More durable, cost-effective pavements can be obtained by inputting more accurate resilient modulus values into the pavement designs. Compared to conventional boring, sampling, and laboratory testing methods, CPT technology provides a reliable, economical, and time-saving tool for site characterization.